Hey, what's up, guys? So previously I talked about the back theory and sigma ring and the construction and the back measure. So in this video, I will introduce what is so-called measurable function. Okay, so let me just write down the standard logic flow of this the real analysis. So basically, it's the stack logic flow of measure theory. Right. So especially for the back measure, so the starting point is that A. You first okay, so step one, right? The step one is that you can define the measure of the interval. Right, basically I should say you can define the back measure of the interval such that let's say, right, so let's say each coordinate is this, and then you define the back measure to be this. In the second, then now you can define a so-called elementary set. Basically, elementary set is the union of finite union of intervals. Okay, so obviously that one can easily compute the elementary sets, right? But just compute the volume. I think you can add the disjoint, right? So, or there at most have some boundary, right? So this is the common, and the third is what we just proved in a previous video, like 14 minutes. You can define a so-called outer measure for each different measure. Let's say mu. So you can define a mu on the elementary set, and then you can prove the previous two results. So let me just quickly read this. So you can define if set A is a union of a countable collection of if there exists an approach to A where A belongs to the elementary set, then we say A is a finitely mu measurable. And if A is a union of countable collection of finitely mu measurable, then A is said to be measurable, mu measurable. Okay, so I will just. Okay, so now if you define the back, you define a standard measure on the back elementary set, then it will give you the back measurable. Okay, so this is the standard step. Okay, so from here you can construct the back measure. Okay, so I would say this is the standard approach by Rudin. If you use the Zygmunt's approach, then it'll be different, and I will introduce in the future videos. Yeah, so I plan to do the two type of the measure theory. One is followed by Rudin. Basically, I give the proof of the abstract measure theory, and I apply to the back measure. And another proof is that you directly work on the back measure. Okay, so let me just give some remark. Some remark I will not prove, some I will prove. I will prove in the future. Okay, so A is very important, right? So if A is open, let's say, so remember that so our discussion is that I only work for RP. Okay, so if A is open, or I mean any topological set is any topological space should be okay. So A is open, then A is measurable. Okay, A is mu measurable. Okay, the reason is that every open set, this is you're at simple set topology. So every open open set in RP is a union of countable open intervals. So remember the countable of union. Okay, so this proof is very simple, right? So you draw a box, you draw your set, and then you create some interval in it. So basically, one idea. Okay, so let me just draw. So one idea is that you imagine that this two-dimensional has its lattice, and you choose each. You choose each cube which inside this space, and once you choose this one, and then you pick out, now you separate the rest into the half, and you keep doing, right? So now this small cube will finally approach to this set. So every open in RP is countable open union of countably open intervals, and by definition, open intervals are finitely mu measurable. So A is a collection, a countable union of finitely mu measurable. So A is measurable. So sometimes when I say measurable, I will skip the mu measurable. Okay. Okay, and so B also remark. Basically, yeah. So the closed set is measurable. Okay, the reason is that the closed set is basically the entire space RP minus some open set. And this guy is measurable. Then by previous data, we proved that measurable is a sigma ring, which is really important. Okay, so which tell you that the intersection, right, and the union or the difference of any two measurable set will give you measurable. Okay. Of any two measurable sets. So let's say, so AB is a measurable, right? Then A union B is measurable. A intersection B is measurable. A minus B is measurable. Okay, so measurable, 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 measurable. Okay, so this is intuitive because measurable means that you can detect its volume. So if A, B are different, then I mean the union should be also and the intersection and difference should be also compute the volume. Okay, so follow from this idea, we can define a so-called Borel set. Okay, so this is a very, let me just maybe write down. So let me define a Borel set. Okay, so Borel set is also, it's very important idea. So you can define a G delta, G is delta. Okay, so let's define G is a set of all open sets. So G is a set of open set in RP. And then we can define F is a set of all closed set in RP. Now I can define a G delta, which is G delta is what? G delta is all the set which is element A. Let's say A is a subset of RP such that A is a intersection of the open set. So G where G belongs to G. Okay, and then you can define F sigma. Basically, is all the set in all the subset in RP such that A can be written as the union. Sigma means union of G, where G belongs to the closed set. So basically, you can define a set to be the intersection of all open set, intersection of some closed set, and obviously that G delta will not the same as G, and they are different, right? So but you can define more. You can define a G delta sigma, basically a set A, which A is defined to be an intersection of G, where G can be written as G delta, and you can keep defining, right? So you can also define F sigma delta, right? So basically, you will have the following: you will have the G and the F, and you can define G delta and the F sigma and the G delta sigma and F sigma delta, and keep going. And by definition, by our results, that GF are measurable, and their countable union, intersection, difference are measurable, right? So the collection or the union of everything is called Borel set. Okay, so the fact is that, so by our proof, the fact is that all Borel set, so the element of this set is called Borel set. All Borel set is measurable. The reason is that the GF is measurable, so their intersection and union, find countable intersection and countable union are measurable, so all Borel set are measurable. Okay, so question, which is obviously, should we ask what? So is all measurable set? Is all measurable set are Borel? So question one. And the second is that is all set measurable? If you're working on the back measure, then the answer of these two questions are both no. Okay, so basically you can find a set find a set which is non-measurable. Okay, so this is a famous Vitelli set. I forget how to spell. Yeah, but I will give you the explanation in the future video. Yeah, this is called a Vitelli set or something. Yeah, it's something V start. Okay, and and you can find a set is measurable but not Borel. Okay, so this guy is very difficult to construct. Right? This is due to we need to introduce the differentiation in the future. So this is use the Cantor's approach. Use a Cantor function. It's not Cantor set. There's a thing called Cantor function. Okay. Okay, and also one very non-trivial fact is that every guy in the Borel set are different. Okay, so this is also the third fact. And every guy in the Borel set are different. Basically, these and these are different, and these are different. Any two guys are different. Okay. Okay, so now let me define also a very important idea called measure zero. Okay, so measure zero means that given a set in RP, and the A is measurable, and I mean the measure zero, right? If measure zero. Okay. Okay, so if A is measurable, then I mean you can talk about measure zero. So if I say measurable, then if I say measure zero, then I already say that A is measurable. Okay, so but this is the non-trivial part is that, or not so non-trivial, is that the set of all measurable set forms the sigma rings. Okay, so you can easily prove this by compute. Let's say I want to compute the intersection of these two. Okay, so reason is that the non-trivial part is that I didn't say that the subset of the measurable of the measure zero sets is measurable, right? But you can prove this by using outer measure. So actually, A intersection B are measurable if both are measure zero, right? But so A intersection B is a subset of A, right? So if you take outer measure, then you get outer measure of A union B is zero, and then you can prove that A is zero. Okay, so now this is zero, right? Because this is zero. Okay, and then this is less or equal to the mu of A. Okay, and then from this you can easily get U A intersection B is a mu A plus mu B minus A intersection B, right? And this guy is zero, and these two are zeros. So these are, so A union B is also measure zero. Okay, so now we prove that it forms the sigma rings. Okay, so also a theorem obviously is that what? So fact is that every countable set in the back measure is measure zero. Okay, so this is a trivial. So I leave you exercise. Basically, you can just take x1, x2, and then label in a one-dimensional, right? And then you now, I mean, it's multi-dimensional is the same, right? I mean, you can since it's countable, right? So basically, you can find a very small box which they don't overlap and cover it, and you can make this box to be arbitrary small. Okay, and but the uncountable set. Uncountable set can be measure zero. Okay, so example are Cantor set. Okay, and the proof is very simple. You can prove that in each step, your Cantor set is less or equal to 3 divided by 2, 3 2/3 to the power n, and for measure, right? And for each, because you can prove that, because by definition your list sets, your outer measure is covered by these intervals, and so you can prove this, and you let n goes to infinity, then it becomes zeros. Okay, so now you prove that these guys measure 0. Okay. Okay, so the key idea is that what we just define the measurable set. So now we can define a so-called measurable functions. Okay, so let me just the step. So the usual step in the back theory is that first you define a measurable set. Now you can define a measurable function. And the third one, you can define the integral of f. Okay, of measurable function and define and give a measurable set. Okay, so now in this video, in this step, I first working on the abstract measurable space, and now final, and I will go to the back. Okay, and okay, to do this, let me just write down the definition. Right, so let's X is a set, right? And then you can take a power set of X, subset of power set as a forced sigma ring, and then you can take mu. So usually this is the standard measurable space notation, such as X sigma mu. X sigma is a sigma ring on X, and the mu is a measure on sigma. And it's called a measurable space. It's called a measurable space. If okay, so basically if sigma is a sigma ring and the mu is a measure. So measure, the condition for measure is basically the non-negative additive set function should be countably additive set function. So remember the big measure contains another property called regular. Okay, so once you have regular, you can define on the elementary set and go to extend. Okay, so one another idea is that if X belongs to sigma, then we call the measurable space. So measurable space need to have the three conditions. The first one, sigma is a sigma ring, mu as a non-negative countably additive set function, which is we call measure. And the third is that X belongs to this. Okay. So the very common example is that you take X to be RP, and you take M to be the volume elementary set. So this gives you the standard back measure. And the another is the probability space. I guess probability space, you can define a sigma as an event, right? So basically for each event, you can attach with probabilities. And the condition is that this P, the total space, the total, should be 1, right? Okay, and let me just introduce a notation. So notation, I introduce a notation called XP. Basically, it's all sets. So X with the property P. Okay. Okay, so now I can define a measurable function. Okay, so definition. Let's say f is a function on some measurable specs x. So you can write this, right? If you are crazy enough, right? But if you're not sloppy, right? But usually people will write just x. So f is a function on measurable space. And to so-called extended real system, basically it can be arbitrary infinity. And f is said to be measurable. Measurable if f of x greater than a. So basically the set x such that f of x greater than a is as a set is measurable for every a. Okay, so this is basically this is called idea of level set, right? So basically, suppose this is f of x, right? sorry, this is not a function. So this is f of x. And then let's say, so basically you pick up some x which is larger than, let's say you pick up this, right? And for each of this guy, which is a measurable for each a. Okay. Okay, so fact. So obviously the theorem, which is a trivial, if you take the look-back measure, if you take your measure, to, let's say x to be RP, and you take your measure to be the back measure. So I use m to be the back measure. Then by definition, right? This you can prove this is open. Sorry, so this is for each a, this guy will be open, right? So please tell you that every continuous function is measurable, because this guy is open, right? So if you inverse, the inverse of the open set will be open. Okay, so sometimes I am very okay, don't worry. Okay, so sorry. Let's go to the theorem. So this theorem is very trivial. So let me just quickly go through. Okay, so our definition starts to x greater than f of x greater than a, right? So so this is measurable. So let me introduce a quick notation. Let me say L of mu is measurable set. I mean, I'm crazy enough, right? So I just say that this is maybe I use this. I use a previous notation. Or maybe I use this. Okay, so these are all the measurable, all the measurable set of mu. Okay, so this is my definition, right? So you can easily check that the following are also measurable. Okay, so the first thing is that f of x greater or equal to a is measurable for every a, and also f of x less than a is measurable. Also f of x greater less or equal to a is measurable. Okay, so the proof is very simple. Let me just write this down. You can write this as f of x greater than a minus 1 over n, right? So for each n, this is measurable by definition. So in the sigma ring, so the countable intersection is measurable. And this is x minus x, f of x greater than a. And then this is x. Right, so this is x, f of x less than a plus 1 over n, right? By definition, this is already measurable, right? And so you can take the intersection. Okay, so and yeah, okay, so theorem. This is also common. So if f is measurable, and the f absolute value is measurable. Okay, so so the converse is not true. Right, but I may tell you in the future why. Okay, should be not true. Okay, so the reason is that say f of x. So I can ask this, right? I can ask what is this, and I can write this as a. So if the absolute value of f of x greater than a, then there's only two ways, right? One is as f of x greater than a, union of x, f of x less than minus a. Then these are measurable. These are measurable. So due to the property of the sigma ring, these are measurable. Oh, sorry, this should be in the intersection. Sorry, yeah, it should be intersection. I'm stupid. Yeah, okay. And the theorem. Let's say Fn is a measurable sequence. Okay. And then I can define a g of x to be sup f of n x, right? Let's say n from 1 to infinity, right? And I can also define a limit sup f of n of x. Okay, so if these f of n are all measurable, so if n is measurable for every n, then g of x, h of x is measurable. Okay, so proof is also the same. So let's consider x, which is g of x greater than a. You can write this, right? This is soup, right? So you can write this each greater than each f of n, right? So sorry, f of n greater than a. Okay, and then you can take h to be inf of gm. Okay, and where gm is basically the soup fn, where n greater than n. So basically, what I want to say is that if you prove the first one, basically the second one is just directly follows. Yeah. So basically, you see, the measurable set has very good properties such that I mean the absolute value and the absolute value and the convergence property basically measurable. So measurable functions are powerful compared to more powerful than the continuous. Okay, and fact, which is easy to prove, that if n or f r g are all measurable. So let me just introduce a notation. So this L mu to be all the functions which are measurable, and the maximum of fg and the minimum of fg are all measurable. Okay, so proof is very simple. So maximum of fg should be what? Should be f plus g plus f minus g divided by 2. And the minimum of fg should be f plus g minus f minus g divided by 2. Okay, and these two are measurable, these two are measurable. Okay, so also, and the limit of the convergent sequence are measurable due to this property, right? Because if the limit is convergent, means that sub f become something. Okay. Okay, and finally, let's say f and g are measurable real value defined on x. So basically, fg are measurable. And then let's say f is continuous on R2. Then let's define h of x to be, let's say, f, right? F of x, g of x. So, but I use two components, right? And let's say x belongs to x. Okay, then h is measurable. So basically, you can, h is measurable. So basically, you can take the two measurable function and put in as a component, and use a continuous map to map it, then it still become measurable, right? So this is non-trivial, very non-trivial. Okay, so obviously, right? So you can, from this you can prove that f plus g is measurable and f times g is measurable, right? Because you can just put a continuous map say f plus g, and you can also put a continuous map f times g, which both are continuous compared to f, right? Because the product is continuous, the addition is continuous. So now you see the measurable function are so powerful that if you act on continuous function by some measurable set and you put in each component, it's still measurable. Crazy. Okay. So proof. Proof is very trivial. So that GA to be UV, FUV greater than A. Okay. So this guy is measurable, right? But important is that F is continuous, so GA is open. So GA is measurable. So GA, the open set in n dimension in the Euclidean space, can be written as IN, which IN is open intervals. Okay, and IN is an open interval, right? So that means I can write IN as a UV. Let's say U less than greater than N less than Bn, and V less than Dn less than Cn. Okay, so now let's consider x, which an less than x and less than bn, sorry, f of x. And this guy is basically, right, just consider x, f of x greater than an, and the union x, f of x less than bn. Okay, so now interesting is that these guys measurable, right? Because these are measurable by definition. So these are measurable. Okay, so which tell you what? Which tell you that sorry. Okay, so which tell you that that what? So which tell you that you can consider x if you consider let's say x and the f of x, g of x belongs to In, right? If it belongs to In, that means that it satisfies these properties. So this belongs to In means that this x, f of x, g of x, this guy belongs to Ga, belongs to Ga. Sorry, what I'm doing. Sorry about this. Let me just let me just rephrase it. Sorry, I'm stupid. I do it too fast. I do it step by step. Okay, so now I have these, right? So these are measurable. So let me just write down these are measurable. Okay, so now I want to ask whether I want to describe this set such that this belongs to In. So if this belongs to In, that means it satisfies its property, right? So basically, it's all a set X such that An less than f of x, Bn, right? Basically, just put U to be f of x, and the intersection with x, Cn less than g of x dn. Right, so which tell you that these are measurable, right, by property. So these guys are measurable, right? So basically, now you can see that the x, f of x, g of x belongs to In are measurable. Okay, so finally, let's consider h, right? So I want to ask x whether h of x is greater than a. This is the same as ask x whether f of x, g of x belongs to Ga. Okay, right? Because Ga is this, right? This is just write down the definition, right? And the Ga is the union of In, right? So which tell you that it's basically a union of the set x belongs to f of x, g of x belongs to In, which these guys measurable, right? By our previous two proof. So which to the measure of the union of the countable union of a measurable set is still measurable. So these guys measurable, right? So which tell you that h is measurable. H is a measurable function. Okay. Okay, so but there's a disguise that's really important that I didn't tell you. Okay, so however, so I will not give the proof of this fact, but this is interesting. So let's say H is a F, right? So if you take two component to this guy, you ask about this guy, right? So let's suppose that the G is continuous and F is measurable. So notice that if F is continuous, then H will be measurable, right? Because continuous measurable continuous is continuous, right? But if F is only measurable and G is continuous, then H is not measurable. It's not need to be measurable, may not be measurable. Okay, so this is the important counter example, which non-intuitive examples I will not talk. Okay. That's it. And next time we will define integral, right? Once we have the measurable function and measurable set, then we can define integral. Okay, so integral basically will somebody give you a measurable function and give you a measurable set E, and you want to describe what the hell is going on, right? What is this? Right? What is this definition? Okay, so given the measurable function, given a measurable set for particular measure, and what do we mean by the integral? Yeah, so our approach is still very highly abstract, at least for the RP dimension. Okay, yeah, and yeah, so these are still very high abstract, and but finally we will go back to the back measure and say something which is some very non-trivial. I mean, doing the stupid mathematics video, nobody cares. Okay, see you guys next video.